we need a specific property to fix our number line. We call it the least upper bound property. The definition is strict. If a subset is non-empty and bounded above, its supremum must exist inside the parent set. It cannot be missing. Let's visualize the difference between a field that fails this property and one that satisfies it. Take our set, A, all positive numbers whose square is less than 2. In the rational realm, Q, the set is bounded, yet it has no tip. The supremum is not a rational number. The property fails. But in the real realm, R, that point, the square root of 2, exists. The supremum is part of the set. In fact, if a set has the least upper bound property, it automatically possesses the greatest lower bound property as well. Let's show why. Consider a set B that is bounded below. How do we find its infimum using only upper bounds? We look at the set L, the set of all lower bounds of B. Since our set S has the least upper bound property, this set L must have a top edge, alpha, also in S. This way, we prove that the top of the lower bounds is exactly the bottom of the original set. Alpha is the infimum. This leads us to an important existence theorem in this chapter. There exists an ordered field R which possesses this least upper bound property. But we do not discard the rationals. The real field R contains Q as a subfield. This new field provides the completeness we were missing, while preserving all the arithmetic and order of the rational numbers we already know. The proof is a lengthy construction process, but it actually constructs R from Q.